All right, so we're doing, looking over some of the StatCrunch and homework problems from chapter 8, chapter 9 today. This does not replace watching lecture videos for the stuff. Like, I'm not doing a whole lot. I'll do some explanations of what's going on, just because it supports doing the homework problems, but you should still watch the lecture videos. Chapter 8, we're doing like the mean of sample means. And then on 8.2, we're doing proportions, the mean of sample proportions. But starting with the mean of sample means for 8.1, what we will find is that the mean of the sample means is the mean of the population. And the standard deviation of the sample means is the same as the standard deviation of the population divided by the square root of n. And don't forget, n is our sample size. So like to kind of help motivate the idea of what's going on here, you'll see in the videos, I reference the IQ test. The IQ test has a mean of 100 and a standard deviation of 15 for the population. And let's say I ask 50 groups of 9 people each their IQ. And then I take the average of each group of 9, or find the average for each group of 9. I get a column, I'll make a column, I get a column of 50 numbers. So the means or the average of each group. Then we find the mean and standard deviation of that group. Of that column. So we're not looking at 50 people, we're looking at 50 averages. We're taking the average of the averages. Does that make sense? So like something that kind of helps, like picture why this standard deviation goes down. Let's say one of my groups, I asked some Albert Einstein motherfucker, and he's like, I got an IQ of 200. I'm like, holy shit, you're an outlier. You're a fucking huge outlier. Like you will be like the number of people you meet like above 130 in your life is relatively few. Maybe 140, above 140. 200, you probably won't meet a 200 in your life. Just flat out, that's how rare they are. So if I were to do a normal mean with them, they cause this huge standard deviation where we get the standard deviation of 15. That's if we just do one person at a time in the mean. But now I say I take Albert Einstein and I throw him in a group with 8 students. Hopefully above average intelligence, but let's assume average intelligence. They all got 100, 100, 100, 100, 100, 100, 100, and along comes his 200. But then we take the average of the 9 people. Now the average is down to like 115, 110. It's still a lot higher than the 100. But his 200 has been completely nerfed. We have like scrubbed his outlierness like out of existence. It still makes like 115 is a big outlier for a group of 9 when the mean's 100. But our standard deviation is how much we're spread out from that thing. So 115's only 15 away from 100. Whereas if we had included him in the original one, he's 100 away from 100 with his score 200. I don't know what his score is. It's really fucking high though. So like the larger one has a larger spread because he's in it. But when we divide by the square root of n, his ability to affect the standard deviation, it just gets washed away. So our mean will still be 100, but our standard deviation for this column of numbers should be approximately the population over the square root of n, which is 15 over the square root of 9, which is about 5. Well, it is 5. So like there's not as much spread when we're looking at the mean of the means. The outliers kind of get whitewashed away. Let's look at a problem in 8.1 on the homework. I'm going to walk through 8.1, number 8 with you. Let me get loaded. I've already solved it, so I got to set it to new numbers. This says a simple random sample of size n equals 64 is obtained from a population that is skewed right with a mean of 86 and a standard deviation of 32. Those all seem like important numbers. N equals 64. Mu is 86. Sigma is 32. And the regular distribution is skewed right. For part A, it's going to ask us the sampling distribution. The sampling distribution, the idea of doing all of these things is to make them approximately normal. So when we do the mean of the sample mean, when you watch the video, you'll see the central limit theorem and how it doesn't matter if we start with a skewed group or a uniform distribution. When we do the sampling distributions of the mean, it makes it into a bell curve, which is great because all of our tests and stuff like that work on bell curves. This first one is the distribution is approximately normal. Then they're going to ask us, what is the mean and standard deviation? The mean stays the same. The mean is still 86. So approximately normal. And then it says mean, ask for the mean. It's the same mean we have, which is 86. It asks for standard deviation and we have to calculate it. A lot of students will enter 32, but it's not. It's that divided by the square root of n. 32 divided by the square root of 64 is 32 divided by 8, which is 4. We're going to use 4. Then it asked me 3 more things. It asked me, what is the probability that X bar is greater than 91.8? What is the probability that X bar is less than or equal to 76.8? And what is the probability that 81.8 is less than X bar, which is less than 92.2? That's the question. And when we go back, I'll show you how we're going to find it all in StatCrunch. And it all depends on this mean right here and this standard deviation here. 86 and 4. Since our sampling distribution is approximately normal, we can use the normal calculator. which you'll find in stats calculators, normal. And we need those values in it. And then we will enter these. Those are the things we'll enter, and it will spit out an answer for us on each of them. So it'll give me there, there, and it'll give me an answer there. Okay, we'll go back. Oh, wait. Sorry, Mariah's still writing. Okay. 1 second. Let me look up something for you guys. All right. So I said we had 86, and we gotta give it the new standard deviation, not the old one. And now it's gonna ask for these things. These are all things we can get in StatCrunch, so I'll do get more help in StatCrunch. And we're gonna go to stats, calculators, normal. We got to enter our mean at 86, our standard deviation at 4. And now we can just change these boxes. For part B, we wanted greater than, and we wanted it greater than 91.8. And it gives me a number, and I'm going to write it down as many decimal places as I can, because I don't remember how many it wanted. That's all we're doing. The computer's going to do all the work for us. The only work we had to do was divide sigma by the square root of n. And hopefully it gives you numbers that you already know the square root of n, like they give you a square, perfect square. But if you don't, you can throw it in a calculator. Then we have the less than. The less than one was less than 76.8. This gives me another number. And finally, it gave me a between. Click on between, and now here for between, up here, this is where we can enter numbers on both sides. This was where the 81.8 goes on the left, and the 92.2 goes on the right. And we click compute, and it gives me another score. 79257019. All right, that's the stuff I need for the problem. Where is my cursor? There it is. I'll come over here and enter those numbers. This was, it says 4 decimal places, 4 decimal places. This was 0.0735. The 4 decimal places on this one was 0.0107. And 4 decimal places on this one, 0.792, it looks like I got to round up, 0.7926. And the questions you're going to see in this chapter are kind of like that. 8.1 is going to look like that. Let's take a look at what happens in 8.2. 8.2, we are doing mean of the sample proportions. And what we're going to find when we do this is that our mean of p hat is going to equal p, the proportion that we get, which is x over n. This is called the point estimate. It's an estimate of the proportion for the population based on the sample. Standard deviation is the square root of p times 1 minus p over n. Now, we need this to be approximately normal so we can use everything we're going to do from here on. So to get approximately normal, two things have to be true for approximately normal. For this to be approximately normal. And you've seen them before. They show up in the 6.1 or 2, the binomial category, because proportion gives you a binomial distribution. We need n times p times 1 minus p to be greater than or equal to 10. And we need b, the sample size, to be less than 0.05 of the population, or less than 5% of the population. For a lot of things, they don't give n all the time. But the population will make it clearly super fucking large. Super duper large. Like it'll say adult Americans. Like adult Americans, there's like, what, 100 million of us? 5% of that's like 5 million. There's no way we're going to get a sample of 5 million. So we can basically assume our sample is less than it. And they don't bother telling you. It's just assumed to be true. But this one we have to check often. We have to check this one a lot. In 8.2, I'm going to do number 2 and number 6. Show you guys those. You guys ready? So 8.2, number 2, I'm going to write down the information and I'll go back over to the document to do some talking about it. It tells me what we're doing is we're describing the sampling distribution. P hat. It says, assume the size of the population is 30,000. That's my big N. Giving me my little n is 1,400 or 1,400, and P is 0.603. Now, if you read through the answers, they all say, they start with the shape of the sampling distribution of P is, two of them say approximately normal, two of them say not normal. And both of them reference the two equations I gave you to check. So what we got to do is check those two equations. So let's check our two criteria. First, we've got n times p times 1 minus p. Is that greater than or equal to 10? I have 1,400 times 0.603 times 1 minus 0.603. Is that greater than or equal to 10? One minus 0.603 is, that one is 0.397. And so I'm looking at 1,400 times 0.603 times 0.397. And I'm getting 335.1. Is that greater than or equal to 10? Yeah, 335 is a lot bigger than 10. Then we check the other one. Is n less than or equal to 0.05? A big N? Is 1,400 less than 0.05 times 30,000. Well, 0.05 times 30,000 is 1,500. 1,400 is less than 1,500, so this one's true. So I want to choose the answer that says approximately normal and has these two equations. NP, 1 minus P, is greater than or equal to 10, and N is less than or equal to 0.05 N. Only one of those has that choice here. I suspect they're going to ask me what the mean and standard deviation are. So let's just calculate them real quick. The mean is just the P. In this case, the 0.603. The standard deviation, I put X, sorry, that's P hat. Standard deviation of P hat is P times 1 minus P over N, and we take the square root. P was 0.603. I already calculated 1 minus P. That was 1 minus P. I'll put that in right here. And N is 1,400. Let me do this in a calculator, see what I get. 603. Nope, there's a missing decimal point. There you go. 603 times 0.397 divided by 1400, and then I take the square root of that. And I'm getting 0.013076451. You guys ready? So the first part, we said the sampling distribution was approximately normal, and that is, for me, A and C both show those. So now I got to narrow down. A says n is less than 0.05n, that's true. C says that also, n is less or equal to 0.05n. Then C says n times p times 1 minus p is greater than or equal to 10, while A says it's less than 10. We don't want less than 10, we want a greater than or equal to 10, so it's got to be C. So this all boiled down, the difference between A and C is just a single sign. One was less than, one is greater than or equal to. You really got to pay attention to the words they use in this class. They like to do this shit a lot. Almost all those sentences are identical. Yeah, there they go. They asked for the mean and they asked for the standard deviation. So the mean was the 0.603, that was the proportion. And we calculated standard deviation to 3 decimal places, that would be 0.013. Okay. Come take a look at number 6. All right, it says a researcher studying public opinion of proposed security changes obtains a simple random sample of 25 adult Americans and asks them whether or not they support the proposed changes. To say that the distribution is of the sample proportion of adults who responded yes is approximately normal, how many more adult Americans does he need to sample? And the question is 15% and 20%. So let's write out what's being asked here. So 8.2, number 6 is on the Social Security. And he's talked to 25 people already surveyed. And they want to know how many more must be surveyed. To be approximately normal. So we had some criteria for that. The criteria for approximately normal was we need n times p times 1 minus p to be greater than or equal to 10, and we need n to be less than 5% of the population. Population was adult Americans. Which is in the millions. Unless n gets in the millions, or really fucking large, there's no way we are greater than 5%. So this one is probably true by default. Unless the n from the left is really large. So we need this to be true. And I don't know what n is. N is the one I don't know. I do know p. P for part A, it says P is 15%. So I'm going to do n times P as a decimal times 1 minus P as a decimal. I need to have that be greater than or equal to 10. So all that linear inequality shit we were doing in class the last few days, this is where we need it. One of the areas we need it. So if I multiply 0.15, this is going to be 0.85. And if I multiply n times 0.15 times 0.85, I get 0.1275 n is greater than or equal to 10. And we just divide by the number. And I get that n has to be greater than or equal to 78.43. I can't ask 78.43 people though, can I? So I would normally round down, but does that work? It's a 0.4, so round down would put me at 78. Is 78 greater than or equal to 78.43? No. So rounding down didn't work here. We got to round up. So we're going to use n equals 79. Now, if you throw in that n, you're going to be told you're wrong because it asked how many more must be surveyed. We need 79. He's already asked 25. So we can subtract that 25 and get 54. That's how many more he needs. Part B does the same thing, but with 20%. You're just doing the same shit and figuring it out. You're gonna do n times 0.20 times 1 minus 0.20 and find n. And subtract, for me, 25. In the interest of saving time, I'm not gonna do it again because it's the same thing. Same work process. And let's face it, you gotta have something to do on your homework. Some fun. So, I will show you, we come over and we put it in. For part A, I got 54 more people. Bam. Then you do part B. I don't know what it is. I'm going to close out. And we will go to the next topic. Maybe I should give you guys a little break because we're going to look at chapter 9 now. So if you guys want to take like a 5-minute break, clear your brain, use the bathroom. We got a viewer at home, they might want to use the bathroom. Oh, Milan's already on her way. She's like, out the door. Let's do it. Guess I could pause the video while we're at the bathroom. Resume recording. All right, so we're looking at chapter 9. Chapter 9 is on inferential statistics. What we're doing in this chapter are called confidence intervals. In chapter 8, we found how to get the mean and standard deviation for something that's approximately normal. This is the shit that we're going to be using. The idea of what's going on here, a normal distribution is a bell curve. So like we did X bar and P hat. I'll use P hat as an example here. So my mean here in the middle was P. And I can go out, if I add one deviation to it, this is going to be another number. This is a number. And I can go out 2 deviations, and this is going to look a lot like the empirical formula chart. We can go 3 deviations that way, or I can go the other way, subtracting deviations. All of this is from our sample, though. What we're trying to infer something about is the actual, in this case, proportion. The actual proportion, it might be here. It might be way over here. It might be right there. We don't know. Like in the last problem here, we had P was 0.603. That was an 8.2. And our standard deviation was 0.013. So if I add 0.103 to this right here, this is like 0.616. And this number here is like 0.629. And if I go the other way, you know, I've got 0.590, 0.577, and I can keep going. The idea is there's numbers along the bottom, but the actual proportion, I don't know, this P here might have been 0.62, like the actual proportion might be 0.621. It might be 0.608. It might be 0.55, way over here on the left. We don't know. All we have is all we have is the numbers we've got. But it's got to be somewhere. And so what we do is we look at like the area between values here. The idea is we're looking at the area under the curve and going, let me write this down. We look at the area under the curve. As a percentage. Remember on the empirical rule, when you're doing the homework, between two deviations was 95%, one deviation was 68%, that kind of thing. We're doing that, but we try to go for like high numbers here. We want high percentages, so we'll look at like 90%, 95%, 99%. We want a lot of area covered. It turns out 90% is plus or minus 1.645 deviations. Which means that's like maybe like right here. And right here. Let's call that value A. And I'll call this like A1 and this like A2. This generates something called the lower limit. A1 is the lower limit or lower bound. A2 is the upper limit or upper bound. So like this area is 90%. %, we kept going calling it 2 deviations, but the actual value is 1.96 deviations. Maybe I'll call that B on the graph. And that'll put like B2 over here and B2 a little bit further out over here, or B1 over here. And C, 99% is plus or minus 2.575 deviations, which is like a little over halfway between the 2 and the 3. So like the 95% would go out to here, and then 99% goes all the way out to here. There's very little left outside the 99%. Look at that little tiny area. That's outside the 99%. It's jack shit. It's not much. It's 1%. So based on these percentages, notice for some of them, like if my red line, or my actual value is this one, all three of these groups contain it. If the actual value is this 0.621, A2, my 90% doesn't contain it. But if I go out to B, the 1.96 deviations, it's in between my two B lines. Does that make sense? This line right here, actual P.621 is right there. It's between my two B lines. So it's in the 95%, but it's not inside the two blue lines. So it's not in the 90%. The idea is the bigger this range is, the more numbers this gets bigger and bigger. So we're more likely to capture the actual value. We never know the actual value though. But we can say how confident we are that we've captured it. And what we say it on is based on these percentages. I could say for A1 and A2, do this on the next page. Like for the 90%, we are 90% confident that the true proportion or if you're doing mean, like we're doing mean in 9.2, we'll be doing mean, but the true proportion or mean for topic XYZ, whatever this distribution is on, is between, well, it's A1 and A2 for the 90% one. I could figure out what that is with these values right here. I had P was 0.603, and I need 1.645 times the standard deviation to figure out the 90%. That's 1.645 times 0.013. That was my standard deviation. I don't know what that is, but let's figure it out. .021385. So if I wanted to see what these values were for the 90%, I draw a little bit more of another empty bell curve down here. I got my 0.603. If I want to go to plus 1.96 or 1.645 deviations, that's where I put in the calculator, right? Yeah. This value is 0.603 plus that 0.02. And to 3 decimal places, this is off the screen. This is 0.624. Minus 0.021385 to 3 decimal places. Going the other direction is 0.582. This is doing the P minus 1.645 deviations. This is my 90%. And that's what I would put in up here. I would say A1, instead of saying A1, I would put 0.582. Instead of saying A2, I would say 0.624. For proportions, alternatively, You could also write it as a percentage. This changes if we want 95%. If I wanted 95%, we go a little bit farther for the 95%. And we're going to do 0.603 plus or minus 1.96 times 0.013. We could do all of this by hand. We don't have to. I'm just illustrating what happens by hand. And if I did this one we would say we are 95% confident. So whatever percentage you're looking for, that's what you're going to say in your sentence. The homework sometimes says one can be 95, not like we are, but it'll say one can be like one, the person can be 95% confident. A little bit more information you need before we like hit the StatCrunch work. Again, this is my upper bound, this is my lower bound. I like to use the abbreviations, or you can use UL and LL, upper limit and lower limit. This distance right here from the center to the boundary is called the error. Well, margin of error. We usually give it an E. It's actually the same distance going to the lower bound too. It's also E. So if I go the full length from the lower limit to the upper limit like this, I go the full length. This is called the width. And notice it's E plus E, which is 2E. So width is 2E. 2 times the error. That's going to come up in some of our problems. One way to find the error, we can find the error by taking the upper limit and subtracting the mean. Or we can start with the mean and subtract the lower limit. Both of them are going to give you E. And one last equation we need. Sometimes they give you, one of the problems, they give you the upper limit and lower limit, and they ask you to find everything else. So if you have the upper limit and lower limit, then mu is add the two together, divide by 2. That's a lot of shit, right? There's a lot going on there, a lot to unpack. We're going to do it shortly in the problems. And I'll bring these up again, but I want to like kind of get it all for you on your page. Say that again? Oh shit. Upper limit and lower limit. Sorry, my bad. Good catch. So let's go look at some problems in 9.1. In 9.1, we're gonna do numbers 1, 2, 3, and 6. And I'll just tell you what number 1 says right out the gate, and we'll look at it in a second. Number 1 says compute the critical value and it says Z alpha over 2. That corresponds to an 84% level of confidence. We're almost there. It's going to ask you to do some bullshit way. You do like the view help, view an example. It's going to give you some tables to look at. It's going to walk you through a fucking bunch of stupid shit. Don't do the view example very often here. This one's terrible. What you want to do is we're going to go to stats, calculators, and normal. Then we will click on between, the between button. We will have something that looks like this. We're going to take that 84% and put it right there. The number you're looking for, Z alpha over 2, appears right there. You'll actually see a negative Z alpha over 2 over here. And funnily enough, this is the one I did earlier, but I'll show you doing it. Your answer is going to be 1.4051 to 2 decimal places is 1.41. Now, you are probably going to have something different than 84%, so you need to see how to walk through it. Did I not fucking click similar question? I didn't click similar question. Yeah, they gave me a different value. They gave me 93%. So mine is going to be 93%, which means I'll put 0.93 here, and I'll walk you through, see what Z alpha over 2 gets for 93%. This is the bullshit. This is what it's going to show you. Look at this shit. Ugh. A table just fucking wall of numbers. This is a pain in the ass. This is how I had to learn how to do statistics. It fucking sucks. Using that table is confusing. Even when you know how to use it, it's fucking confusing. We're going to go to Get More Help and StatCrunch. And we go stats, calculators, normal. And click on between. And I'm going to come down here and I'm going to say, I want 93% right here. Notice that I get 1.8119 and negative 1.8119. It's the positive one. So to 2 decimals, this is 1.81. That's what's going to ask for here. Next question, let me do a similar question so it gives me different numbers. Next question says, determine the point estimate of the population proportion, the margin of error for the following confidence interval, and the number of individuals in the sample with a specific characteristic X for the sample size provided. So, and I'll write them down on the next page, and we'll do the calculations there. So number 2, they give me the lower bound is 0.128. The upper bound is 0.442. And they give me n equals 1200. They asked me to find A, the point estimate, B, the margin of error, and C, X. Well, when you have the 2 bounds, we can do this by adding them up and dividing by 2. I'm getting 0.285. This is our P, it's also our mu. It's the same thing as our mu here, or mu of P. The margin of error, remember we can do the upper bound minus mu, or lower bound, or mu minus lower bound. We do either one. I'm going to do the upper bound minus lower bound. I'm going to have 0.442 minus 0.285. And it is 0.157. That's my margin of error. So I'm going to use that value. That'll be part B. X comes from the equation P hat equals X over N. We have P hat now. We calculated it. It's 0.285. I don't know what X is, but N was 1,200. It was given to us. If you multiply both sides by 1,200, you'll get X by itself. So whatever this denominator is, multiply both sides by it. 1,200 times 0.285 is 342. X is 342 for my problem. All right, you guys ready? No, you're done writing. Your pins are moving. Stop moving. I'm going to come over here and enter the things I found. I said P was 0.285. I said error was 0.157. Nearest thousandth is 3 decimal places. I'm doing the right thing. and we calculated X at 342. All done. Question number 3. A similar question. So number 3 is on construct a confidence interval for me. It wants 90%. It gives me X equals 75, and it gives me my N equals 150. Now we could go through and we could find P, we could find, which is our mu, then we could find sigma. We're not gonna do all that. No, 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 don't do this. Don't do this by hand. What we're gonna do is we're gonna do stats, proportion stats. And then you're given some options. Proportion stats comes with 1 sample or 2 sample. These are both options you get, and they both lead to the same options down here. There's 4 of them, but the 3 that we really care about is with data, with summary, and one says power sample size. We're going to do a problem that uses the power sample size one in a bit. What we're doing here is with summary. With data would be having each individual's response and finding out if it's yes or no, you know, true or false, like it or don't like it, whatever it is. When you do stats, proportion stats, 1 sample with summary, what it gives you is it says number of successes, and there's a box. This is where we put X. Number of observations gives us another box, and that's where we put N. Then there's a little button that says hypothesis testing. And we're going to do that shit in chapters 10 through 13. Well, 10 and 11. And then there's going to be a little circle that says confidence interval for P. We're going to fill in that button. And there's going to be a little field that says level. This is where we put our percent as a decimal. My X was 75, my N was 150, and they asked me for 90%. They're probably going to ask you something different. What it will spit out is it will spit out a lower limit and it will spit out an upper limit. We're just going to pull that from StatCrunch, and that's what our answer is. You guys ready? Oh wait, no, sorry, you're still ready. Go ahead and finish if you're done. Okay. Proportion stats, 1 sample. I'm gonna show you a couple fields real quick before we do it. See how we've got 1 sample has got with data, with summary, power sample size. It says the same thing for 2 sample. This is good. That's going to be something we're going to do in chapter 11. T-stats is going to be 9.2. One sample has the same shit. Two sample has the same shit. Paired is different. Paired requires data. You don't have any choices. But like 9. Everything up from now on, a lot of it's in the exact same areas. Hypothesis testing is what we're doing in the 10.1 or chapter 10 onward, and that's one of the circle buttons as you'll see in a second. We're doing one sample with summary. I had 75 and 150. Hypothesis test is the default one. That's not the one I want. We're going to use that for chapter 10 onward. Confidence interval I want. The default is 95%. We want 90% for my problem. And it gives me a lower limit of 0.0408248829 and an upper limit of 56715,087. I don't remember how many decimal places I need, but I can always double check. You can also double check right here on the screen that you've got the right stuff. Notice it says 90% confidence interval. That matches what I'm looking for. And it shows me my count and my total. My 75 and 150 show up here. So I could tell by looking at this that I had the right information on it. To 3 decimal places, the lower bound or lower limit was 0.041. And the upper bound was 0.567. I screwed something up. I think I got an extra decimal here. I think that, yeah, it's not 0. It was 4, it's 408. I'm like, that looks like a really, really large interval. All right, let me go back and look at it. If you get that, you should always just go back and double check. 75, 150.
I think you were reading the one that said standard error.
Did I? Oh shit, you're right. I was. Good call. Thank you. 432849113. I'm sure that's what Malaya was saying, what you were saying. It's super fucking quiet. Cody's voice booms. All right. So 433. Notice it gives us this fucking table of critical values. We don't need any of this shit. This is like telling you if you wanted to do it by hand. Don't do this shit by hand. Finally, question 6. Actually, before I finish with question 6, we got some numbers here. I want to talk about what we would do here. Here, we're like in a normal situation and like on your final, you'll be given a lower limit and upper limit. You'll be given the confidence interval and you'll be told what it's about. Like say it's like the percentage of students that use Snapchat or some shit like that. We will say we are 90% confident that the true proportion for the topic, and you should put what the topic is, not just say for topic, is between 0.433 and 0.567. Alternatively, because that sounds weird, you could write 43.3% and 56.7%. You can turn it to a percentage if you want. That's gonna be one of your questions on the fine. Different problem, different numbers, with the exact setup. And that's how other questions of the homework have it too. Okay, number 6. Number 6, I'll show it to you in a second. Number 6 is on abolishing the penny. That way you'll know you're on the right topic. And my question says, what size sample should be obtained if he, we're talking about a researcher, wants the estimate to be within 4 percentage points with 90% confidence if A, he uses a prior estimate of 26% or previous estimate, and B, he does not use prior estimates. Okay. What size sample? What it's telling us to do is find N. That's our job. Find the sample size. To do this, we're going to do stats, proportion stats, one sample, and this is where we choose for power sample size. It'll pop up a window. Up here, it will say hypothesis testing, and one will say confidence interval. You definitely want to click on the confidence interval one. And then it's going to have, when you do that, you'll have some boxes here. This will say confidence level, and we'll have a box. It'll say target proportion, and we'll have a box. It will say width, and we'll have a box. And it will say sample size, and have a box. And finally, a little compute button. There's also a nice big picture of a chart. I don't know what the hell a chart's for. Not really all that helpful. I said 90 confidence, 90% confidence. There we go. So what are we filling in from the problem? The confidence level is given, it's 90%, so 0.90. The width, remember, that is 2 times the error. The error is the percentage points. E is 4% or 0.04. So this is 2 times 0.04, which is 0.08. That's what goes in the width. That's going to be the same for both A and B. Those don't change. The only thing that changes is what you enter in this box. For A, in this box, we're going to put 0.26 because it gave us 26%. And for B, when you don't use a prior estimate, you use 0.50. So you're either putting 0.26 or 0.50 if you're doing A or B. N will pop up here. And that's what we're looking for. So for A, I'll have N equals something. For B, I'll have N equals something. And you can do them at the same time in the calculator. So you're not clicking back and forth between windows, which sucks. Or you can click back and forth between windows and spend your very precious remaining minutes before the final on Monday. Let's go take a look at it. Again, don't get tricked by their fucking blue shit. This is not going to help you. You do not want to use one of these tables. No. No, 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 no. To get more help, you go to StatCrunch. You're doing stats, proportion stats, one sample, power sample size. I'm going to click on the confidence interval width, and I just set everything I want in here. My confidence interval is 90%. My target proportion starts off at 0.26. And my width is 0.08. It gives me my sample size is 326. Notice that it changed the width. The width doesn't say 0.08, but it's a number really, really, really close to 0.08. What they did is they changed the width so that the sample size is a nice round integer. So when I do part B, I gotta change this to 50%, and you're gonna wanna reset the width to the correct width. So part B, target proportion, 50%, width is 8. Sample size is 423 for part B. So I got 326 and 423. I will come over here and enter those in. One more section, 9.2. Let's talk about some of the stuff we'll use in there real quick. So 9.2 is the same shit as 9.1, really. But for sample means, not sample proportion. So both of them say stats, then you're either using proportion stats or t-stats. T-stats is for the means. Sample means is going to go under t-stats. Proportion stats is obviously proportion stats. Then you have a bunch of shit that's in common. I showed it to you a second ago. You get one sample as a choice. You get two sample as a choice. These have with data, with summary, power sample size. There's one other one. I've never used the other one, so I'm not even going to bother to write down what it is. The t-stats has one additional one. It's called paired, and it doesn't use any of the other shit. This is just in T. Chapters 10 and 11. We'll use all of these. But with the circle hypothesis test clicked, not confidence interval. Calculating P is pretty easy. And when we're doing proportions, we use the normal calculator to find things we're looking for. If you need to calculate T, and you will on one of the problems because I'm going to show it to you. We're going to go stats, calculators, T. All right, you guys ready? We're going to do a few problems in this section. Problem number one says determine the t value for each case. For A, on the one, I've already did A with the other group. I'm going to do B with you. A was find t value such that the area in the right tail is 0.25 with 14 degrees of freedom. Part B says right tail is 0.15 with 26 degrees. And they're going to ask you some more things. I think there's a C, a D, there's a bunch. But it's all doing the same thing. And all of these, you're going to go to stats, calculators, T-stats. Not T-stats, just T, sorry. Stats, calculators, T. There will be a box, it might say DF, it stands for degrees of freedom. There's a box to put a number in. Then it will have X. I don't know why it has X. It should say T. It should say T, but it doesn't. It says X, there's a drop-down box, and there's a field, and then equals another field over here. This is where your T is going to appear. If you're looking at the right tail, you want to use the greater than sign. If you're looking at the left tail, which I think they asked in like C or D, you're using the less than sign. And there might be a between. If there is a between, the between box is at the top. So that's where you choose whether or not you're going to put greater than or less than. Your degrees of freedom go in here. Part A had 14 for me, part B has 26. Here is where I put the percentage for the right tail or the left tail, or whatever it says. For me, for A, it was 0.25. For B, it's 0.15. And you'll see it all in a second when I load the screen up. Okay. Again, they give you some red herring shit. Oh, let me click on this. And again, you get this fucking table. It's terrible. You know how I know when students don't watch my lecture videos? I get fucking email after email after fucking email saying, I don't know how to read the table. I'm like, maybe fucking attend lecture or watch a lecture video and I'll show you how to do it. I'm not gonna teach you that shit because it's tedious and it's not helpful. It takes way too long. You don't walk around with a fucking, this table here. But if you have a job like this, you will have access to statistical software. Your employer will probably have it for you already. It may not be StatCrunch, it probably isn't. But they all do the same shit. You put in numbers, you tell it what you want to do, you just have to learn how to do it in that particular program. So for us, for this problem, we're doing stats, calculators, T. Degrees of freedom. For part A, I had 14. And I wanted greater than for right tail. And I had 0.25. See where I got the 0.692? Then they changed it to 26 degrees of freedom. And they wanted this right thing to be 0.15. And so here I will have T will be to 3 decimal places, 1.058. before I click back and put it in, they're gonna ask you more, but I'm not gonna go back through the rest of them. Like if you notice, it says right tail and the red's on the right. You can tell by the color on this whether you have the right tail. If it asks for left tail, it should look like it's on the left. The red's on the left. For between, they might ask you to put in between. They might say, what's 0.85 or some shit like that. And they'll ask you which values go there. So they'll and again, you're just pulling these values from right here, going off what prompt you put over here and what degrees of freedom you put in here. That's all that's going to go on in problem 1. This was 1.058. See, now it wants left t-value, different degrees of freedom. It says use symmetry. The use symmetry is if you're using the tables, because it's designed to be negative on the left and positive on the right, and they only show the positive numbers. But if you just put it in StatCrunch, it'll tell you. All right, let's go to ticket number 2. I already did this one, and I had already clicked similar question, and it reset at 0. That's why it's got that big red X. I didn't do it wrong. I know what I'm doing. So, this says the data from a simple random sample with 25 observations was used to construct the plots given below. The normal probability plot that was constructed has a correlation coefficient of 0.953. Judge whether a t-interval can be constructed using the data in the sample. And there's a bunch of drop-down shit. Does not suggest, suggests. We have inequalities here. Let's go to the camera, document camera, and talk about what you're looking at where. So this was 9.2, number 2. And I had 25 observations. It told me the correlation coefficient is 0.953. And whether a t-interval can be constructed or not, interval can be constructed. Depends on if the group comes from a normal group. If the population is normal. Like bell curve normal. So there's 2 criteria for this to happen. For this to happen, the box plot cannot have outliers. And for part B, the correlation coefficient, this is from chapter 4. This is like a lot of this stuff from right here is from chapter 4. The correlation coefficient needs to be greater than the critical value. And the critical value is based on the number of observations. There's a table for it. So here I've got 0.953. It's greater than, we gotta look this up for n equals 25. We're gonna look it up. And we need to check if box plot has any outliers. That's what we're doing in the pictures on this one. This one we actually have to click on the blue shit. Most of the time we don't. We're looking for the red, like for this, the red dots should be between the blue lines. That's not really the one, like this shows up in the correlation coefficient information. What we're looking at here is the box plot, and the box plot has an outlier. So we're already fucked. We can't use a t-distribution. So the box plot, it does have outliers. Let's check the critical value because they want us to fill in a bunch of shit in a sentence. Critical value for sample size n, we had, for this problem was 25 observations. 25 is 0.959. And we were comparing that to 0.953. So 0.959 is going to go here. 0.953 is actually less than 0.959. And the box plot has outliers. So we want to say that we can't do it. T interval cannot be constructed because it doesn't meet the criteria. And this one, it does not suggest the data comes from a normal population. So this is, we're going with the negative outcomes. I'm going to go back, click similar question here so that, because I'm going to go over it now. I probably won't go over this in the other class. We've done stuff with lower bound and upper bound and finding the population mean, the margin error in proportion. We did this in proportions. It's the same thing here, okay? A lot of these questions are similar. I'm not going to walk through this problem. I'm going to show you what it looks like when you do it. So like some of the problems are going to give you a confidence interval. They're going to give you a sample size. They will tell you what X bar is, and they will tell you the standard deviation. So what we're going to do when you're doing it, I want StatCrunch. There we go. We're going to go stats, t-stats, one sample with summary. Shit. God damn it. It gives me the sample mean is 105. It gives you this standard deviation was 10. And depending on which one you're doing, A, B, or C, you have a different confidence level and a different sample size. So you're going to go through and set the sample size, and you're going to click on confidence interval, and you're going to do the confidence interval. And they have you looking at different ones, and you're looking at like the answers, and later on, at the end, you're going to compare them. But this is what you can expect to see when you do the t-stat one, rather than proportion stats. So proportion stats asks for X and N. Here it asks for the mean standard deviation in N. The one I want to walk with you guys is number 7, because from number 5, you will see that it asks, it really, a lot of this beginning stuff is fluff. It boils down to provide 2 recommendations for decreasing the margin of error. Just as we saw, remember the margin of error is the distance from here to here. The distance from the center to where you're going. The bigger percentages were further out. So if we want a smaller margin of error, we need to make the percentages smaller. Does that make sense? That's where one of these is going. Decrease the confidence level. The other one is based on, remember how we were doing the standard deviation divided by the square root of n? When you divide by the square root of n, dividing by, as that number gets bigger on the bottom, that square root gets bigger on the bottom, and it makes the overall standard deviation smaller. And the standard deviation is how the margin of error is determined. So you can decrease the confidence level, or you can increase the sample size. That's what you're looking for on this one. The rest is just fluff. The rest of that sentence. On that number 5 you were just looking at, or just had up here, they actually have you see that. On A and B, you have a 98% confidence interval for both, and they have you change the sample size. And so you can see that by going from 16 to 12, what happens with the confidence level? Or what happens with the margin of error? As n goes down, the confidence level goes up. The margin of error goes up. It's backwards. As n goes up, it goes down, and as n goes down, it goes up. The percentage matches. As the percentage gets higher, the error gets higher. And you'll see that when you compare, they'll have you compare A, 98% and n equals 16, to C, 90% and n equals 16. So you'll do some comparisons and you'll see what we just talked about in number 7. Do you guys have any questions? If you want to see all that shit written down or like in your notes, I don't want to rewrite it. It's the same as what I had before. It doesn't change. The problem is identical. No matter how many times I click similar question, the important shit doesn't change. All right, other than that, tomorrow we're going to be looking at doing stats and proportion stats, or proportion stats, t-stats. We're going to do a little bit from 1 sample, 2 sample, and paired for, and then proportion sample, 1 sample, 2 sample. We're going to talk about the 5 steps of the hypothesis test, and we'll do at least 5 different examples. If I have time to do chapter 12 and 13, I'll hit chapter 12 and 13 as well. Then on Thursday, practice final. I'll show you what to be expected. The words are like, the numbers are different, the questions are different, but the categories are all the same. You will find that we are going to have 2 confidence intervals. One is based on proportion and one is based on mean, just like you're doing in chapter 9. Then there are 8 hypothesis tests that we cover in this class. And there's going to be 8 questions, 1 for each hypothesis test. So we'll talk about strategies for like doing the test on Thursday. I think you guys will be in good shape if you've been following along here, getting your homework done. Don't forget, if you want extra credit on the exams, do 70% of your homework. I'm not adding it in till the end. I have to download everything at the end after everyone's done. But I'm going to be saying, did you do 70% for the midterm? If you did, I'm adding percent to your homework. Did you do it on the, let's see, let me come back over here. Let's look at the syllabus real quick. Canvas, there we go. That's what I want. You can read about the extra credit thing in the syllabus under leveling up. It's in there about how to get extra credit. So, other than that, I will see you tomorrow. Godspeed. Get the fuck out. Whatever floats your boat. Any questions, Guadalupe?
No, thank you.
Okay, I'll see you tomorrow.